So hi everyone, in today's talk, I'm going to introduce our recent work about end-to-end efficient quantum thermal and ground state preparation. Basically, we will propose some simple quantum algorithms to prepare the thermal state and the ground state. Basically, this is a collaboration work with Yuntao Zhang from Caltech and my previous postdoc mentor, Professor Lin from UC Berkeley, and Professor John Practical from Caltech. And in the first part of this talk, I will give a quick introduction about this problems and the previous algorithm for solving this problem. So, in fact, the problem statement is very simple. Here, we assume that we have a Hamiltonian capital H and the inverse temperature beta. And our goal is to prepare the thermal state of this Hamiltonian capital H, which takes the form exponential minus beta H over its trace. Okay, this is called the thermal state. Now, when we let temperature go to 0, meaning that we let beta go to plus infinity, this thermal state will converge to the smallest eigenvectors of capital H, which is also called the ground state of my Hamiltonian capital H. So in this regime, preparing the thermal state is often is almost equivalent to preparing the ground state. Okay. So in fact, the thermal state and the ground state preparation problems has a lot of applications in different areas. For example, in quantum chemistry, we can use this state to study the energy landscape and the correlation effect of a given molecule. In quantum physics, we can also use this state to study the superconductance effect. And in the literature, we have a lot of traditional algorithms for preparing the ground state and the thermal state. Here, I only want to introduce one of them, which has theoretical guarantees. This is called the QPE-based algorithm. Basically, in the QPE-based algorithms, we have an initial state phi, and then we can try to draw the energy landscape of my initial state phi. Here is pi, and so it's defined to be the initial overlap between my initial state phi and ith eigenvectors of my Hamiltonian. Okay, then the QPE-based algorithm is essentially a filtering algorithm. After we apply the filter functions to this energy landscape, in the resulting state, we can only see the ground state. Then we only need to do a measurement. We can get the ground state. Okay. However, the success probability of this algorithm is upper bounded by the initial overlap between my initial state and the ground state of this Hamiltonian. And in a lot of the cases, this initial overlap can be 0 or even exponentially small. Then in this case, so the success probability will be very low, and the number of repetitions will be exponentially large. So this algorithm is not that efficient if my initial overlap is very small. Okay, so for the thermal state preparation problems, we can also use the QP idea to solve it. In this case, to construct the thermal state, we basically wanted to prepare a purified thermal state on our quantum computer. This purified thermal state is a pure state. However, if you trace out the first ancilla qubit, so the first set of the ancilla qubit, you can essentially recover the original thermal state. And using QPE algorithm, the computational cost to prepare this purified thermal state scales as a square root of 2 to the power n over the normalization factor c beta. Okay, and this essentially means if we want to guarantee this algorithm is efficient, we require this factor scales as polynomially in the number of qubits. And in a lot of the cases, this basically means we require the inverse of beta, the temperature equals to scales as a polynomially in the number of qubits, which is a very high temperature regime. Okay, This is in fact not very good. So because the QP-based algorithms has several disadvantages. Now, in this talk, our main goal is try to partially solve these two questions. First, we want to find an algorithm to efficiently prepare ground state from arbitrarily small initial overlap P0, and we want to do it for general physical and chemical Hamiltonian. Second question is, we want to find an algorithm to efficiently prepare the thermal state at a constant or low temperature. Again, this is for general or chemical Hamiltonian. Okay, these are two questions we want to solve. And in our recent work, we propose a simple algorithms to partially solve these two questions. Here is a quantum circuit of our algorithm. Okay, I will first briefly introduce our algorithms and then post the detail in the later part of this talk. Basically, we have an iteration algorithms, and in each step of my algorithms, I need to run this quantum circuit. And in this quantum circuit, I will couple my density operator with a single ancilla bus. After that, I will run a total Hamiltonian simulations to this coupled systems for certain time capital T. After the Hamiltonian simulation, I will trace out my environment to get rid of the bus information. Okay, then I get a quantum channel that can map my density operator rho n to rho n plus 1. This is a discrete quantum channel. Okay, so basically, in our work, after choosing this total Hamiltonian and rho e property, we can guarantee that this rho n will converge to our target thermal state or ground state after we apply this quantum. After we apply this quantum channel enough number of times, basically rho n will converge to sigma beta when I let n go to plus infinity. And for some physical Hamiltonian, we can also rigorously show the convergence rate. This is basically a sketch of our algorithms. In the later part of this talk, I will share more details about it. Okay. And up to now, any question? Okay.
Hi Zhiyan. I have a basic question. So I guess the single ancilla bath is in a single qubit thermal state, like ket 0 plus e to the minus some beta ket 1 by square root 2, something like that.
Right. So exactly. So here you can see that for our total Hamiltonian, I chose the thermal state to be a single qubit C only acting on the bus, and this rho E is essentially set to be the thermal state of this bus Hamiltonian.
Right.
Yeah, you are exactly right.
And these W's, I mean, it's not very clear what these W's are. So your model is like the collision model. It looks very similar to the collision model, where you are kind of having a single qubit bath. You're evolving like the Hamiltonian in an interleaved manner. It has some features of that, but this W part is not clear to me. What is this?
Yes.
Yeah.
Right. So in our algorithms, this W is actually a free variable you can tune. And in our algorithms, we will often sample this W from a random distribution. So in fact, I will introduce how to choose the W in the later part of my talk.
All right. Thank you. Yeah.
Okay. Good. So then maybe I can continue. Okay. So now, before introducing the details of our new algorithms, I want to introduce the Lindblad dynamics-based algorithms, which is actually a very popular algorithm framework in the last few years. By showing how the Lindblad dynamics-based algorithm works, we can get some intuition about why we want to use the system bus interaction system to prepare the ground state and the thermal state. Okay. In fact, the Lindblad dynamics algorithm is inspired by the open quantum system. In the open quantum systems, we have the system part, which has our original Hamiltonian and the density operator. We also have a very large environment part, which has its own Hamiltonian and the density operator. Furthermore, there is some interactions between my systems and the environment. This finally gave us the total, the total system Hamiltonians and the total system density operator. Then, in the evolutions of the open quantum systems, we only care about the evolutions of the system density operator, meaning that we do some total system evolutions for this couple of systems for certain time t. Then we will always trace out the environment part and only care about the evolutions of my system density operator. Okay, which is rho st here. Okay, so here when we care about the open quantum system, the main the main reason is we all know nature thermalizes very fast. Here you can imagine that I put a food into a fridge. Then what I can do is I can see the food as my systems and the fridge as environment. And we know that the temperature of my food will quickly convert to the temperatures of my fridge. Okay, so intuitively, this means that my system density operator will converge to a thermal state with the inverse, with inverse of beta, same as the temperatures of my fridge. And since nature thermalizes fast, we can expect this convergence rate will be very fast. Okay, based on this idea,
sorry, can I quickly ask what quantitatively one means by fast here? Is it like inverse polynomial linking? Is that what we should think about? Or?
Oh yeah, so here for example, when you have a fridge, then that fridge has a temperature, and the inverse of temperature is our beta.
Right. No, I was asking like how do you quantify fast?
How do I quantify fast? Yeah. This is a very good question. So in fact, because we want to prepare the thermal state and ground state efficiently, we say that this convergence rate is fast if it scales polynomially in the number of qubits. This is called fast, and in the later part of my talk, you will also see some word called rapid. So rapid means that the convergence rate is actually polylog in the number of qubits. This is called rapid mixing.
I see. So it's not really about the temperature; it's about the system size.
Yes.
What we care about here.
Right. So. Yeah.
One comment, which it should depend on the spectral gap of the Lindbladian, right? Because that's what you're doing. You're kind of mixing you're kind of creating Lindbladian dynamics, and you're kind of waiting for the system to mix. So it's kind of like it should depend on the mixing time of this things, which is like 1 over the spectral gap of the Lindbladian, right?
Right, exactly. So later, after we construct the Lindblad dynamics, if we want to rigorously give an upper bound to the mixing time, we need to characterize the spectral gap of the Lindblad dynamics. And at that time, what we need to do is we need to study how the spectral gap of the Lindblad dynamics scales with the system size.
Right. Yeah.
Yeah. So you will also see this in the later part of my talk. Okay. So basically, this is the intuitions of the algorithms. Now, since in the open quantum system, the thermalizations can happen very fast. The basic idea is we want to design some algorithm that can mimic this process. And basically, we want to design an algorithm that working as a fridge on my quantum computer. Okay, so this is the intuitions of all the algorithms in this area, and this is actually where the Lindblad dynamics come from. So in the literature, we can show that the linked blood dynamics is an approximation to the open quantum system. In fact, using the Bohr, Markov, and circular approximation, we can show that the system density operator from my open quantum system can be approximated by the solutions of the linked blood dynamics. In this linked blood dynamics, there are three different terms. The first term is called the coherent term, which essentially corresponding to the original Hamiltonian evolution. And the last two terms are called the dissipative terms. Here, this Ka is a matrix. We often call it as a jump operator in our linked blood dynamics. Okay, basically, in the literature, people can rigorously prove that when we have this kind of approximations, the solutions to the open quantum system can be approximated by the solutions of my linked blood dynamics. However, in practice, sometimes these approximations might not be true, meaning that the linked blood dynamics is not always a good approximation to the open quantum system. Okay. However, in the algorithm design, we don't care about this. Now, the story is when we want to prepare a thermal state or ground state, we essentially view linked blood dynamics as an algorithm tool. So we basically construct the linked blood dynamics as an algorithm to prepare the thermal state and the ground state. Okay, and this idea has originally been proposed by Zhifang Chen in 2023. Their papers was recently published on Nature. So in the last few years, we have done a series of work to further simplify their idea and extending their ideas to the ground state preparation case. We have proposed some algorithms for simulating the linked blood dynamics, and more recently, we also have our work characterizing the mixing time of the linked blood dynamics, both numerically and theoretically. Okay, so now I want to quickly show you how the linked blood dynamics is constructed and how it works. Basically, so to solve this problem, we want to construct a linked blood dynamics to make sure that the solutions can converge to the targeted thermal state or ground state when we let t go to infinity. And I want this to be happen for any initial state, so that my algorithm does not require a good initial state. Okay, and under this setting, there are two problems I need to solve. The first one is how to choose this matrix G and the matrix capital K. And next, after I choose G and K, what is the simulation cost and what is the convergence rate? I basically need to answer these two questions. Okay, so here, to save some time, I will only talk about the ground state preparation case. If you are interested in the thermal state to preparation case, you can check our another paper. Okay, so in the ground state preparation case, the coherent term is very easy to choose. I can just choose G equals to the Hamiltonians or just G equals to 0, which is very simple. The jump operator looks slightly more complicated. However, you can essentially imagine it as a linear combination of Heisenberg evolution. This Ft is the coefficient of this Heisenberg evolution. We can call it the filter function. This matrix AA, so this AA is a matrix. We often call it the coupling operator. Okay. The beautiful thing is when we construct this jump operator, we only need to make sure that the Fourier transform of my function f equals to 0 on the positive axis. Then as long as my function f satisfying this condition, the ground state is a fixed point of my linked blood dynamics. Okay, so to ensure that the ground state is a fixed point of my linked blood dynamics, I only need to choose a function f satisfying this condition, and we have a lot of freedom to adjust this function f and also the coupling operator AA. So there is no restrictions on the coupling operator AA. We are so we are free to choose this operator. Okay. Here we can first look at a very simple example. So now my Hamiltonian capital H is just a minus z, a single qubit system. Okay. Then in this case, I choose my coupling operator A to be x. then we can show that I can find a filter function f such that the corresponding k equals to 0, 1. Basically, this matrix k will map one state to the 0 state. And I choose my coherent term equal to 0. Then by doing some direct calculation, we can show that the ground state of my capital H, which is the 0 state, is actually a fixed point of my linear dynamics. Okay. So we can also do some further calculation to show that if my initial state equals to one state, so here, if my initial state equals to one state, then the initial overlap between my initial state and the ground state is actually 0. There is no overlap with the ground state. However, if you plug the initial state into my linear dynamics, we can show so we can exactly solve the dynamics and find the formulas of the solution. So according to this formula, we can see that this rho t will converge to the ground state exponentially fast. Okay. Although here we only consider one initial state, this property is actually true for any initial state. So we don't require a good initial state to ensure the success of our algorithm. And furthermore, since the solutions to the linear dynamics is always a density operator, the whole dynamics is a trace preserving. So in my algorithm, there is no post-selection process. The success probability is always 1. This is also one advantage of this algorithm framework. So here, I only talk about the ground state preparation case. If you are interested in the thermal state preparation case, you can check our another papers on CMP. Okay. So now I have answered the first question, which is how to prepare G and K. Next, I will talk about the simulation cost and end-to-end complexities of the algorithm. So I noticed that there is a question on the chat. Do we need time evolutions of system Hamiltonians to compute the jump operator K? And so yes, this is a very good question. So in fact, the answers to this question is in the next slide. Yeah. So basically, now we already know how to construct this G and K. The next question is how to simulate my linear dynamics. So in fact, to simulate my linear dynamics, the first thing I need to do is I need to find a block encoding of the coherent term and my jump operator. And in my simulation, I assume access to the Hamiltonian evolution and the block encodings of the original coupling operator AA. Then in our papers, we propose an efficient way to construct the block encodings of these two terms. It basically relies on this quantum circuit. So to save some time, I'm not planning to tell you how to construct this block encodings in detail, but it only relies on the Hamiltonian simulations and the block encoding of AA, and we can efficiently do it. Okay. So
Zhiyan, sorry to interrupt you. I have a more basic question. So I understand that, given the block encoding of UAA, you can construct the block encodings of G and K. But my question is a bit more fundamental, which is that, suppose you want to find the ground state of a given Hamiltonian by this route, right? So how easy or difficult it is to find these G's and K's? Do I need to run some classical algorithm to get to G's and K's, because I need that in order to construct these to run the algorithm? Yeah.
Right. So this is a fantastic question. I would say the main advantage of this algorithm is how to find this G and K is very simple. So as I mentioned before, for the ground state case, I only need to choose this G to be the original Hamiltonian or equal to 0. Since we already know the original Hamiltonian, so there is almost no construction here. And to construct the jump operator K, I only need to choose my function f satisfying in this condition, which is also very simple. So I do think the most beautiful thing in this algorithm framework is it's very easy to find this G and K, and also it's very easy to efficiently construct CR block encodings on the quantum computer.
Right, right. Okay, this is helpful. Yeah.
Yeah. Okay. Good.
Can I also ask a quick question since we are already interrupted? So I was expecting a sort of statement somewhere that gives a ceiling with the system size. I may have missed it. So we're saying that you use this dynamics, and then I guess at some point you can say that it converges to the correct state, and the error gets really small as a function of the system size. Is that how it's going to be, or because in the example, of course, it was exactly the case, right? So that was fine, but in the general setting, like I just wanted like a statement that shows the convergence in terms of the temperature and the system size.
Right. So in fact, in the later part of my talk, I will introduce the end-to-end complexity of our algorithms, and there you will see where the system size dependence come from.
Okay. Sorry for the interruption. Thank you.
Yeah, it's okay. Okay. So now I have already tell you how, I have briefly tell you how to construct the block encodings of the cohort term and the jump operator. So then, in fact, after we have the blocking encodings of these two terms, the existing literature has already provided a lot of efficient algorithms for us to simulate the Lindblad dynamics. Okay, so rough for complexity to solve the Lindblad dynamics up to time capital T scales, so the complexity scales as almost linearly. So in the simulation time capital T and the polylog in 1 over epsilon. So here there is almost no system size dependence. And this epsilon is the simulation accuracy we require. And the simulation complexity scales as linearly in the simulation time capital T. Okay, so now this is where the system size dependence come from. So basically here we have our Lindblad dynamics. And we know that the solutions will converge to the thermal state when we let T go to plus infinity. But we need to go to characterize how long it takes the solution to converge to the thermal state. And basically, we need to answer this important question: how large is my capital T? Okay, so this capital T will finally enter my the end-to-end complexities of this algorithm framework. Okay, so in fact, this is not a simple question to answer. So simply speaking, this capital T is upper bounded by the mixing time of my Lindblad dynamics, and the mixing time characterizes how long it takes for the solutions to evolve close enough to my fixed point. Basically here, if I define T mix in this way, I can guarantee that for any given initial state, you evolve the Lindblad dynamics for time T mix, then the resulting state will be epsilon close to my target state. If I choose my epsilon to be small, then I can ensure that the resulting state will be very close to my target thermal state or the ground state. Okay, so this essentially because my previous complexity scales linearly in the capital T, now I only need to find an upper bound for this capital T. Then I can guarantee that my algorithm is efficient. Okay. However, theoretically, rigorously characterizing the mixing time of the Lindblad dynamics is very hard. In fact, we all know that for the ground state preparation problems, in the worst case, this problem is QMA hard. This essentially means, in general, we don't expect we can prove the mixing time scales as a polynomial in the number of systems for all the Hamiltonian. However, we do want to show that for general physical and chemical Hamiltonians, the mixing time can scale polynomially in the system size. Okay, so So in the last two years, we do have for some exciting progress in these areas, and in our more recent work, we basically propose some method to characterize the mixing time for the ground state preparation, both numerically and theoretically. So here I want to show you some quick results. So in our papers, one example is we consider the TFRM model with a boundary dissipation. The boundary dissipations meaning that I only put my coupling operators on the boundaries of my lattice. Okay.
So what does TFRM stand for?
TFRM IM stands for transverse field IC model.
So Hamiltonians. Thank you. I'm new to the area.
So Hamiltonians essentially takes this form. And I want to emphasize that this is not a commuting Hamiltonian. This is actually a non-commuting Hamiltonian. Okay. So and here we use the boundary dissipation, meaning that I put the coupling operator only on the boundary of my lattice. Okay. Then numerically we can show that any question?
Zhiyan, yeah, one point. So if you could prove that the mixing time here is order of n cube, that is good. But if you just take this Hamiltonian, if G and J are constants, I think the spectral gap of this Hamiltonian is a constant.
Right.
So then if I go with the conventional route of preparing, like using this filtering technique, then the dependence on the spectral gap is going to be a constant, and so your complexity would become just 1 over overlap log, etc., etc.
No. So in fact, I disagree with the second argument. So in fact, if you so you do the filtering idea, the spectral gap is not the main difficulty. The main difficulty is the initial overlap.
Right. So the dependence would just be 1 over the overlap, right? Order O tilde of 1 over the overlap, right? That would be the complexity.
Yes, but you cannot guarantee that the initial overlap is good.
Right. That is true. That is true. But
right.
I still have, if I want to beat this algorithm, I still so capital N here is the number of spins, right?
Yes, number of spins. Yes, right.
Okay. So then, I still think that this is better, because I don't think you can prepare very easily an initial state with 1 over this amount of overlap, I think.
Right. So the key point of this algorithm framework is we don't require a good initial state. As long as we have a linear dynamics, you start from any initial state, the algorithm can still work. Okay. Yeah. So basically, numerically, we can show that when we increase the number of qubits, the mixing time scales as the order n to the cube. So in fact, in our papers, we also propose a technique to theoretically prove this mixing time scaling. So we can rigorously prove that for this particular model, the mixing time scales as order n to the cube. Okay. So since this mixing time is a polynomial in the number of qubits, we call it a fast mixing. And the second example is we can consider general 1D local Hamiltonian. And if we use bulk dissipation, meaning that I put coupling operators on all the lattice, okay, then we can show that when we increase the system size, the mixing time can be log in the number of qubits. This is a very fast mixing time, and we often call it rapid mixing. So in our papers, we can show this numerical result for general 1D local Hamiltonians, and in the perturbation regimes, we can also rigorously prove for this rapid mixing time. Okay, so these are the two mixing time results in our recent paper. They are also other the result. If you are interested, you can also check this paper. Okay. So now I will go to the last part of my talk. Now I think you are pretty convinced that the linear dynamics-based algorithm can help us to prepare the thermal state and the ground state. Then the question will be, why we still care about the weak system bus interaction-based algorithm? So the answer so it's actually because of simplicity. So first, I want to introduce the early fault-tolerant quantum computer. In fact, the early fault-tolerant quantum computer is a quantum computer we can expect in the near future. Since this is an early quantum computer, we can only expect limited useful quantum resources on this quantum computer. This means that to run algorithms on this quantum computer, we need significantly simplified algorithms for near-term and practical deployment. Also, the end-to-end complexity of the linear dynamics can be efficient. The implementations of these algorithms is always difficult. So, when we implement the linear dynamics, we need to find a way to construct the block encoding of my G and the jump operator. This can be complicated and not early fault tolerant. Okay, so in fact, our work is the first work that can simultaneously rigorously prove the fixed point error bound, has the missing time guarantee, and also friendly to the early fault tolerant implementation. And this is based on the weak system bus interaction system. Okay, so to introduce the intuitions of these algorithms, we recall that previously we see linear dynamics as an algorithm tool to prepare the thermal state and the ground state. Okay, so now to make our algorithm even simpler, the main idea is we get rid of the linear dynamics. We directly look at the original open quantum system. So in fact, here we want to directly use the system bus interaction system as an algorithm tool for us to prepare the thermal state and the ground state. And because the open quantum system is always a physical system, it will be much easier to implement this system bus interaction systems on our quantum computer. Okay, so the main reasons we want to propose a new algorithm framework is because of simplicity. Then there are still two questions I need to answer. First, how to set up the interaction system to prepare the thermal state and the ground state. And second, what is the simulation cost and the convergence rate of my algorithm? Okay, so then to answer the first question, I need to tell you the details of our algorithm. Basically, as I mentioned before, in each step of my algorithms, I need to run a total Hamiltonian simulation, then do a trace-out process to get the updates. Okay, in our papers, we give a specific form of the total Hamiltonian simulation, which contains three different terms. Okay, so the first term is my original Hamiltonian, only acting on this part. And my main goal is to prepare the ground state or the thermal state of this Hamiltonian capital H. And the second term is single qubit C, which only acts on the ancilla bus. Okay, and this omega is a free variable for us to tune. Okay, and the third term is in the interaction term. This alpha is a number which corresponding to the interaction strength between my systems and the bus. This function f t is similar to the filter functions in the linear Gaussian setting. And this AS, this matrix AS is also similar to the Coffin to the Coffin operator. So in the linear Gaussian setting. Okay, so basically, in our algorithms, we need to construct the total Hamiltonian in this way. And the same as before, this AS is a free variable to choose. You have many different ways to choose this coupling operator AS. And so in each step of my algorithms, I will trace out and reset my bus density operator. And intuitively, so in fact, in our work, I will always set my bus Hamiltonian, so my bus density operator to be the thermal state of my bus Hamiltonian. This setup is a very intuitive. This is so essentially in my open quantum system, I try to fix the temperatures of my fridge. Then the temperatures of my system will naturally converge to the temperatures of my fridge. Okay, so this is basically how I choose my time-dependent Hamiltonians and the bus density operator. And here I also want to give some detailed choice of different parameters. So in my my total Hamiltonian, there is the function, the filter function ft, and in our wallpapers, I choose this ft to be a Gaussian interaction function, where sigma is a very large number. Basically, you can imagine that I have a flat filter function ft in the time domain. Okay, and this omega will be chosen from a random distribution. This random distribution can be very flexible. For example, one good way to choose this random distribution is a uniformly sample omega from the interval 0 to 2 times the norm of h. This is just one way to make the choice. In practice, you can also use other choices. And the choice of AS is also very flexible. We basically can choose AS uniformly from a random set. Some good examples will be if we are in the spin system, then we can often choose AS uniformly from the single poly set. And if we are in the fermionic system, we can choose this AS uniformly from single creation or annihilation set. So here, I want to emphasize that if I want to, if I choose AS uniformly from the single poly set, then the third interaction term will just be local operator. Meaning that in my Hamiltonian simulation, if I want to implement this third interaction term, this will just give you local co-gates. Okay, then the Hamiltonian simulations, so the evolutions for this total Hamiltonian will only contain the original Hamiltonian simulations, and all other gates are local gates. This can be very efficient and very friendly to the near-term or even analog quantum computer. Okay, so here in our algorithm, because we only do the Hamiltonian simulation, the simulations of our algorithms is essentially equivalent to the Hamiltonian simulations and the trace out. And in our papers, we mainly propose to use the second order charter to do this time-dependent Hamiltonian simulation. The main reason is the second order charter only involves the forward Hamiltonian evolution. This is friendly to the analog quantum computer. In fact, if you use a second order charter, our algorithm can be implemented on the analog quantum device. Okay, and because we use the second order charter, the complexity scales as a t to the power 3/2 over square root of epsilon. The main advantage of our algorithm is we don't require any ancilla qubit, and there is no need to construct the jump operators in our algorithm framework. This is much simpler than the linear biodynamics framework. Okay, so and next, if we want to talk about the end-to-end complexity of our algorithm, we need to go back to the missing time. Here, the first term is just the simulation cost of single step of our algorithm. But this is an iteration algorithm. So to characterize the end-to-end complexity, we also need to consider how many iterations we need to do. This is actually related with the missing time of my quantum channel phi. Here, since I have a discrete quantum channel, so we need to define the integer mixing time. Basically, this mixing time characterizes that how many times I need to apply my quantum channel phi to make sure the resulting density operators is closer to the target state. Okay, this definition is similar to the definitions of the mixing time for the Lindblad dynamics case. And in our work papers, one main contribution is for some physical model. So we can provide a way to upper bound this mixing time. Okay. Now I want to propose. So I want to briefly introduce the main result of our paper. The first main result is we can show that the algorithm can efficiently prepare the ground state or the thermal state under the fast mixing assumption. In the first theorem, we can show that given a finite beta, we can prepare the thermal state with end-to-end complexity scaled as a polynomially in beta, the top mix and 1 over epsilon, where epsilon is the approximation precision. In our algorithms, we need to choose sigma to be sufficiently large and alpha to be sufficiently small. So in our papers, we can rigorously tell you how large this sigma needs to be and how small this alpha needs to be. And for the ground state case, we assume that my capital H has a spectral gap delta. Then I can prepare the ground state with end-to-end complexity polynomially in 1 over beta and the top mix and still 1 over epsilon. Okay. Then, in fact, according to these two results, you can see that as long as my top mix is not very large, meaning that I have a fast mixing, this algorithm can efficiently prepare the thermal state and the ground state, and there is almost no system size dependence. In fact, the system size dependence will mainly come from the top mix. So now, to give a rigorous end-to-end complexity, we also need to provide an upper bound for this top mix. And this is actually the second main result of our paper. So in fact, our work is the first work that can rigorously prove the mixing time for certain physical Hamiltonians under the weak system bus interaction framework. So in all the previous works, so they can provide an algorithm, but they don't have rigorous mixing time guarantee. Okay, so here in our papers, because of technical reason, we consider a rescaled mixing time T mix equals to alpha square time tau mix. The main reason comes from our analysis. So in our analysis, we can actually prove that this quantum channel is similar to we apply a Lindblad dynamics with time alpha far squares to the density operator rho. Okay, and this alpha square give us intuitions to rescale the mixing time. Yeah. Any questions?
Yeah, I'm sorry. What was alpha? Is it just a parameter, or does it? I'm sorry. Can you remind us?
Yeah. Right. Good. So this alpha is actually the interaction strength between the systems and the bus. This is a free variable to tune. Yeah. So this is essentially a parameter that we can tune.
Okay. Thank you.
Yeah. And in our work, because we need to choose alpha to be very small, this is why we call it weak interaction system bus system interaction system. So in fact, if I can choose alpha to be very large, then we will have a strong interaction system. Okay.
And does it have any consequences on how easy it is to implement whether we are in the strong coupling or weak coupling regime? Does it translate into ease of implementation?
Yeah. Right. So I do think this is a very good question. So in our papers, theoretically, we can only show that 1 alpha is very small. We can efficiently prepare the thermal state and the ground state. However, there is no result telling you that the strong interaction does not work. We still have some hope to show that the strong interaction can still work for this system, but this will depend on very very different analysis technique.
Thank you.
Yes. Yeah. So basically, in our papers, because we are in the weak.
I have a question. I don't know.
Yeah. Sure.
Yeah. So can you show me the total Hamiltonian again? Like
the total Hamiltonian. Yeah. Here's this part.
Yeah, so I from the interaction picture, like I think the AS corresponds to the jump operator. Like if you like
Uh,
like prepare like corresponding Lindbladian for this, right? Like by
yes.
taking the Born approximation, right? So
Uh, no. So first, in fact, I prefer to call AS as the coupling operator. So if you write it into the Lindblad form, there is a transformation between AS and the jump operator.
right.
Right. So here I prefer call AS the coupling operator instead of the jump operator. So if I go to the previous page, so the previous pages, so this KA is the jump operator, and AA is the coupling operator.
I see. But in the Lindbladian case, like you need this Hamiltonian simulation and Fourier transform. So like how do you get rid of this in the
Right.
like this single ancilla algorithm?
Right. So I do think this is a fantastic question. So in fact, you can see that in the Lindbladian framework, so the complicated thing is we need to construct this jump operator, right? However, in the weak system bus interaction system, we don't need to construct this jump operator. So actually, as long as I choose my total Hamiltonian in this form, I will automatically have this jump operator when I do the approximation. Everything is automatic. I no longer need to construct these jump operators in my algorithm. This is the most important advantages of this new algorithm framework.
I see. Yeah.
Yeah. So in fact, if I want to tell you how this works, then this involves a lot of detailed calculations. However, you can essentially go to our papers. In our papers, there is a very detailed derivation telling you that to just using this Hamiltonian, why why this can give us the correct jump operator. Mm-hmm. Okay.
Yeah.
Good.
So
Yeah, good.
one follow-up question. So if I
Yeah.
look at this from the like the collision model perspective, like the Hamiltonian that you have used corresponds to a Lindbladian, and
Mhm.
I am not sure, but I think the Lindbladian for this will like directly have the AS as the jump operator, or so if I like use the Lindbladian approach, like the Lindbladian algorithm, and use AS as the jump operator, will it prepare the Gibbs state, or
No. So if you directly use AS as the jump operator, it does not prepare the ground state or the thermal state. So the key is if you derive the Lindbladian dynamics from say the total Hamiltonian, the jump operator is different from AS. The jump operator will actually take the form of KA before.
I understand. Okay.
Yeah. So this this is the key of this derivation. Yeah.
I think one way to think about this is, as you know, for many cases, this will just be sigma plus sigma minus. Just, kind of just a single, like a ladder operator. That's it, I think. So you can just write it as a single qubit sum of Pauli's, like sigma x plus I sigma y by 2, something like that.
Right. So this is also the reasons why the implementations of this algorithm is very simple. The interaction parts are essentially local gates.
I agree.
Okay. Yeah. Okay. Yeah. So then maybe I can continue to finish the missing time part. So basically, in our papers, we consider the rescaled missing time, and for different Hamiltonians, we can show that this missing time scales polynomially in the number of qubits, meaning that we have a faster mixing. So now, if I plug this missing time back So back into my previous complexity result, I can finally show the efficient preparations of the thermal state and the ground state. Okay, so here, one thing I want to emphasize is in our papers, although we have rigorous mixing time guarantees, all of these systems are very simple. Very simple systems. We do want to see that whether this framework can be extended to more complicated and more general physical systems. So according to our numerical experiments, we do think this is possible, but there are still a lot of technical difficulties. Okay. So in summary, in this talk, I introduced the system bus interactions algorithm framework. I also tell you the blood dynamics based algorithm for the thermal state and ground state preparation. These two algorithm framework share some similarities, but we do believe the system bus interaction framework can be much simpler than the Lindblad dynamics framework. So overall, in this area, although we have made some concrete progress in the last few years, there are still a lot of open problems to be understood, and I do think all of these open questions are very important and interesting. Okay, so here are some references for this talk, and thank you for your time and listening.